Hello everyone and welcome to this lecture on negative feedback. The outline of today's lecture will be the following. First, we are going to introduce the negative feedback superposition model. Then we are going to talk to a variation of this model that it is called the asymptotic model, which is much more suitable for analog circuit design. Then we are going to talk about the ideal amplifier that we will call the nuller. And then we are going to introduce basic negative feedback configurations. The last point of today will be the frequency response in negative feedback systems. So the negative feedback model can be presented in the following way. We have an input that enters to a system, and this input can take two paths. There may be one path that goes directly to the output of the system here, and one path that goes inside. And this part we call it an attenuation. This is an input attenuation. And then it enters to an amplifying stage that we call it A here. It enters to an amplifying stage, and then it can go towards the output, and then it can be attenuated before it arrives to the output. And this amplifier is connected through another network that we call beta. Is the feedback factor in the following way, and it is added here. So there is an addition that happens here. And when we calculate the total transfer function, we call it the transfer function AT from the input to the output. That will be out divided by in. We have that the AT0, that it is the direct transfer or the feed forward path, comes directly. That doesn't come as a surprise. And then everything else that it is here will add the following term that we have here. Okay, so we can do very quickly this small term, which is interesting to take a look. We have our factor beta here. We have our amplification here, and then it is going to the output. So let's assume for a second that we don't have these attenuation terms, this one and this one. That only happens in, let's say, in particular cases where we have large distances or large traces, large connections, then they will have those. Otherwise, these terms will always be equal to 1. So let's assume for a second that they don't exist, and then let's analyze this system here. So we have that we can take that the input here plus the output multiplied by beta. Okay, so we have this adder here. All this will be multiplied by the amplification A. So, and then that will be equal to the output. That will be our transfer function here. So now we can expand this. It's going to be equal to out beta A. Sorry, that will be plus, and that will be equal to the output, and that will be equal to 1 minus beta A, and then we have that the transfer function will be equal to A divided by 1 minus beta A. Okay, so that is this part that we have here. So something important in the negative feedback system, beta is always lower than 0, is a negative number. Okay, so when we have a negative number, we can rewrite this equation like this. So that will be our equation for the transfer function. Okay, so we are going to analyze this equation. We have that the total transfer function depends on the feed forward, and depends on the term that has the feedback here. And this is quite good for doing theoretical analysis, and it is pretty much used for that. But it doesn't bring much insight for the analog circuit design. And the reason for that is that when we do analysis using this equation, we have the following problems. Let's take, for instance, this example. We have a non-inverting amplifier that is built with an op-amp. This op-amp will have some amplification A, and then the feedback will be implemented using resistors. At some point we will need to break the loop in order to do the analysis using this equation, and then we need to select where to break the loop. One option is to break it here. So this is what we have done here. Introduce a test voltage here, and then follow the loop in this direction. That is one option. Another option will be to break the loop here, as I have done here, and then analyze all the loop here in this direction. But anytime that I introduce these breaking points in the loop, I am also introducing inaccuracies because the loading effects. For instance, the input impedance of the real amplifier has some value, and then when I am disconnected from the network that brings beta from this resistive divider, then I will be introducing some mistake. Here is the same. The load and the output impedance of the amplifier has been disconnected from R2, and then I'm going to introduce inaccuracies. So this is one of the problems of trying to use this equation directly to get beta. So in the theory, there are several ways that people have tried to solve this problem, and you will find that depending on the type of amplifier, it's possible to use different modeling using zeta, Y, G, and 8-port networks. But there are many situations in which none of these work. For instance, this is an interesting example. This is a circuit that has 2 loops. Then where to break the loop in order to get the feedback factor beta. So there are these kind of cases, and they are very, very common, in which we cannot really use these techniques in which we model the amplifiers as different port networks. Now, instead of using directly the original model, we're going to work on it and on the superposition model, and get something that it is much more useful for analog design. So we start from the superposition model that we just presented, and then we are going to assume that this term it is going to be infinite. Okay, let's assume that we have an ideal amplifier that produces the infinite AB. Okay, we call it AB the loop gain. So let's assume that it creates an infinite loop gain. So under that assumption, and I'm going to call this this transfer function AT infinite, okay, or the asymptotic gain, because it assumes that we have an infinite amplification available. So when it is infinite, basically we can disregard this term, this disappear, and as I mentioned before, the terms that we have for losses, we can disregard it in analog integrated circuits at low frequency. So this will be 1, and this will be also 1. So there will not be attenuation. The distances that we have, our connections are very, very small, so there will not be attenuations. And then, although always present the feed-forward path, for simplicity we are going to assume that this is equal to 0. Okay. So under those assumptions, we have that the asymptotic gain, the ideal gain, will be approximately equal to 1 minus 1 divided by beta. Okay, that will be the asymptotic gain. Then I can rewrite this equation. Okay, under this assumption, we have the AT equal to A divided by 1 minus A beta, and then I can multiply this by beta and divide it by beta also here, so it doesn't change. And then my transfer function, as I saw when I make it infinite, that will be equal to minus the ideal or asymptotic gain multiplied by A beta and divided by 1 plus A beta. Okay, so let's put an example to make it a bit more easy to understand what is this A beta. So we have an amplifier. Again, we take our example, the non-inverting amplifier that we discussed before. So if this is R1, this is R2, this is V in, and this is V out. We know that if we assume that the amplifier is ideal, or transfer function V out divided by V in equal to, or total transfer function will only depend on the resistors. This is from our basic course on analog electronics, so that will take this value R1. So that will be our ideal transfer function. Now the beta, it is actually coming from this network that I have added around the amplifier, and in this case it is formed by two resistors, R1 and R2. How we calculate beta, and also very often in the basic course on analog electronics we just break the loop, and this is one of the very few times that we're going to do it here, because as I mentioned before, it lends to errors due to loading. In this particular case the amplifier is ideal, so we don't introduce. So many errors, but in practice it is not really easy to do. Put Vx here, and then we have in, we have V in, we have V out here, and then we can calculate our beta here, or we can calculate here a beta as the whole gain in the loop. So that will be the gain in this loop. Okay, and that will be equal to A multiplied by this voltage divider, R1 plus R2. Okay, so clearly we have that this part, it is what we call beta. And beta, if we take into consideration or transfer function for the ideal case, so we have that beta is equal to 1 over AT. Okay, so we have that very clear relationship between the ideal asymptotic gain. We can calculate directly only by taking a look to the feedback here, and we can actually rewrite the complete transfer function like this, or like this, and that is something interesting, because now I can start a design procedure that it is based on this equation. So we will have two steps. The first one, it is to design and the feedback that I will need, assuming that my amplifier is ideal, okay, and that I will just need to put which kind of components I need in the feedback network, and the assumption that the amplifier is ideal. And afterwards I will need to find how to implement a beta, that is, how to implement the amplifier. That will be the second step, so that we have an adequate a beta value that introduce very low error, or on the other we call it a little bit different, we can doesn't introduce inaccuracies, so we have a high accuracy. So I will have to decide how good this my amplifier has to be in order to introduce low accuracies. The ideal amplifier has a name. I will call it the nuller. So, and we need to introduce formally the nuller. So the nuller is a two-port network, and we have already talked a little bit about the two-port network. We have here, it is input voltage, we have here input current, we have the output voltage, and we have defined the output current like this. And then we have said that the equations that govern the two-port network from we consider this a ABCD two-port network will be the following, and E in is equal to C B out plus D E out. Okay, so we have these equations, and then this is an ideal amplifier. An ideal amplifier, all the ABCD parameters are equal to 0. They are equal to 0, so remember that the gains are 1 over the ABCD parameters. For instance, the voltage gain is equal to 1 over A. The transconductance gain, G, is equal to 1 over B. the transimpedance gain zeta t is equal to 1 over c, and the current gain AE is equal to 1 over d. So for an ideal amplifier, these parameters are 0, so that they make the gains infinite. So we have these ABCD parameters for the nullor, and this is the symbol for the nullor: plus, minus, minus, plus. And it has some properties. The first one we have just discussed. The nullor has infinite gain, an infinite gain in all parameters, ABCD, for all source and load combinations. So that is property. Second, it provides signal inversion. So you see, I have put at the input plus minus and at the output minus plus. So I can take a negative output if I want. So I have available a negative output. And the third one, it provides subtraction at the input. Okay, so this plus minus means that it has a differential input. It means that there is subtraction at the input. So basically, I have all the ingredients to implement the negative feedback. So we have gain, and then we have an addition subtraction at the input. So I can implement this addition of a negative quantity at the input. So these are the kind of things that I need to be able to implement the following system. So we have a lot of gain, and I can take a negative quantity from the output and add it at the input. So with that, we can implement the negative feedback. Now, how do we use the nullor? There are many possibilities that we have for using the nullor in order to design negative feedback amplifier, and one, it is use transformers. Transformers are made using coupled inductors, and but they are not pretty much used in analog circuit design, at least at low frequencies, because the inductors are very huge, so they cannot be easily integrated. However, at radio frequency and several gigahertz, those inductors are small. A few nanohenries of hundred of picohenries are possible to integrate, and then you can make transformers at radio frequency. So, but that is a radio frequency, several gigahertz. Generators are also possible, but they are very noisy components. But it is possible to use generators. We are not going to study generators in this course, but it is one possibility. We can use active devices, transistors, to implement the negative feedback. So this is one possibility. But most of the time you will see that the negative feedback systems include passive devices, and the reason for that is that passive devices are intrinsically linear components. Resistors, capacitors, inductors are much more linear than active devices. Okay, so if they are very linear, then as we saw in the previous example here with this non-inverting amplifier, if my resistors are very linear, then the whole transfer function will become linear, assuming that we have a lot of loop gain. They will only depend on the gain will only depend on the resistors. If they are very linear, the whole transfer function will be very linear. So something that we saw in the previous lecture is that amplifying devices, transistors, are intrinsically non-linear devices. So in order to create or design linear amplifiers, we will prefer to use passive devices in the feedback. So there are many situations in which you have negative feedback with active devices, and we will introduce some of these examples. So if we assume that we are going to use passive impedance as part of the feedback network, we have a few ways in which we can do the connections. We have the first one is the voltage amplifier, and this is exactly the example that we typically use in analog electronics. We do the connection of a non-inverting amplifier here, like this. This is a voltage amplifier using this configuration, V in and V out here. Conceptually, it works like this. There is a nuller here. For an ideal amplifier, we can replace it with a nuller, and then we take a positive output, feedback to the input through this resistor divider, and then we get the following transfer function. Okay. Then properties here. There is infinite amplification here. Amplification here is infinite. All the ABCD parameters are 0, so there is infinite amplification. When there is infinite amplification here, there are some interesting situations that arises. There is another property that no current enter in the nuller. It has infinite input impedance, and when we have the nuller as an ideal amplifier and negative feedback, we have that this voltage becomes 0. Okay, the difference at the input, the subtraction in an ideal amplifier, in the ideal negative amplifier, is always 0, because we have that this system corrects itself to the feedback, and then it puts the input voltage at both sides equal to 0. Okay, then we can easily do calculations here. The voltage here will be V in. This V in will produce a current that flows through theta 1. There is no current flowing here, so the current flowing here is 0. But the current flowing here is also 0. So all this current, V in divided by theta 1, has to pass through this component also. And then we can calculate easily the output voltage will be equal to V in plus V in divided by theta 1 multiplied by theta 2. So V out will be equal to V in 1 plus theta 2 divided by theta 1. Or the voltage gain will be like this, exactly the same. We can do the same for the other amplifiers that we have. We have a transconductance amplifier. The connection is the following. We have the nuller here, and we connected the positive output of the nuller and the input together, and then an impedance to ground. Again, same situation. First we check, we have negative feedback, plus it is connected to minus. This voltage difference is 0 volts, which means that we have V in also here. This V in is going to produce a current equal to V in divided by theta 1. And then there is no current flowing in this direction. This current is 0. That means that all this current V in divided by theta 1 must flow in this direction here, the output. And then it has to flow also all this current in this direction, because this is part of the output port. Now, if you see very carefully here, this current has an arrow going down, so it is the opposite direction as we have defined the two-port network current going out of the system. So it means that this current is negative, so it gives us the following transfer function. So it will be that E out divided by V in will be equal to minus 1 divided by theta 1. Okay, we have also the current amplifier here. Same situation, we have an input current, and this voltage is equal to 0 volt, voltage difference here. There is no current flowing in this direction. All this current, it is going to flow like this and produce a voltage difference here, and then we will call this voltage Vx. So this is 0 volts, it is ground. This is going to be also 0 volt ground. So Vx will be equal to E in times theta 1 and with a minus sign. Okay, it will be a minus sign here because this is 0 volt. So we have Vx, and now we can calculate what is the current that flows here, and then we do know the analysis there. This is current, it is also going to be E out. This current flows inside the amplifier and goes out like this with the same sign. So how do we calculate that current? So we use node analysis. So we have Vx, this voltage divided by theta 2 plus Vx divided by theta 1 and plus E out. This has to be equal to 0, and now we can group this. This will be 1 theta 2, 1 theta 1 plus E out will be equal to 0. That means that E out will be equal to, and then there will be minus Vx. That will be theta 1, theta 2, theta 1 plus theta 2, and then we replace this part here. That will be equal to minus in theta 1 times theta 1 plus theta 2 divided by theta 1 times theta 2. Theta 1 disappears, theta 1 disappears, and then we have at the end that E out divided by E in, and that will be equal to theta 1 plus theta 2 divided by theta 2. Okay, that is exactly what we have here, and that is how we do the calculations for these stages. We have a last one here, the transimpedance amplifier. Same story, we have that the voltage here is 0. There is no current flowing in the ideal amplifier, so all this current has to flow through the load, to the feedback resistors, feedback impedance theta 1. So what we have here is that this is 0 volts here. That means that we calculate what it is, this P out is going to be minus E in times theta 1. B out divided by E in is going to be equal to minus theta 1. Okay, those are going to be the gains of the basic amplifying stages. There are other common configurations besides the 4 main configurations, and one very popular is the following: the inverting voltage amplifier, and for sure you have seen it before in other analog basic course. An inverting amplifier can be designed using an op-amp, and 2 resistors. This is V1 and this is V2, V out. So that can be conceptually done using a transimpedance amplifier and one resistor that it is in series. Okay, so we can use this topology also. Same thing here. This is 0 volts. Here means that the current that is passing here will be equal to V in divided by zeta 1. There is no current flowing here. It means that all this current will be directed to zeta 2 and produce a voltage drop here. Also this V out will be equal to, if this is ground, this is 0 volt, the voltage that we have at the output is going to be negative, and it is going to be equal to the current is this times the impedance, and V out divided by V in is going to be equal to minus zeta 2 divided by zeta 1. Okay, we can actually do it in a different way. We can also have a voltage amplifier using also transconductors amplifier. The difference between these two is actually that the input impedance here is not very high, which causes some trouble, of course. So one alternative is to use this topology, and then we will call this one load, actually zeta load. And then in this particular case, as we saw before, the current flowing here, it is equal to V1 V in divided by zeta 1, and this current is going to flow like this also. So V out, and it's going to produce a voltage drop in this direction. V out will be equal to minus V in divided by zeta 1 times zeta L, or the transfer function will be equal to minus zeta L divided by zeta 1. Also, producing some inversion and amplification depending on the value of the resistors. We have another interesting topology. If we connect the nuller in the following way, like this, we have that this voltage here is 0 volts. That means that we will have V in directed to the output. So V in is going to be, in this case, equal to V out. V out divided by V in is going to be equal to 1. So this works like a voltage follower. Very high impedance at the output and zero impedance at the output, so you can drive very well small loads. If we connect it on the other hand like this, we can use this configuration as a current follower. So we see that there is no current entering here. There is 0 volts between these two terminals, but there is no current entering in the nuller, so all this current has to be diverted towards this output here, and then enters the nuller and then goes out like this. So E out is going to be equal to E in, and then we have that E out divided by V in is going to be equal to 1, and we call it this one a current follower. So besides the configurations that we have just introduced, there are many other configurations of negative feedback. There are some that are very interesting, and they are called indirect negative feedback configurations. We are going to just study a few of these ones that are very common in analog integrated circuit design. So we have seen that we can use the nuller to introduce negative feedback. We have also talked about that we are going to use active devices that provide amplification. These active devices can introduce errors, can be nonlinear, etc. So one way to linearize these devices, it is to use negative feedback. So that is not a surprise. We're going to implement amplifiers with active devices. But a very interesting situation, very useful, is that we can actually linearize or reduce the error in active devices that are not inside the loop. Every time that we do this, we will call it indirect negative feedback. And here we have one possibility. Okay, so we have this device. This can be a transistor, for instance. This can be a transistor that is inside a loop. And then if we take a look this configuration that we see here, the configuration that we see here, it is exactly the same as we saw here. Is a current amplifier. Okay, this is a current amplifier. Same configuration, but beside the amplifier that we have, an ideal amplifier, we have our device. It can be your transistor. It is inside this loop. Yeah. So we say that we put a negative feedback around this, and then we linearize the current that passes through this component, and we reduce the errors that are created by this component when it is inside the loop. Now the voltage or currents that are controlling this device, this is a two-port device, at the input of the port, you can just copy these ones and connect it to another device that it is not inside the loop. And the idea here it is that all the corrections that are done to this device here will apply also for this device. So later during this course we will introduce the current mirror, in which we can just with one single current create as many current replicas with different amplitudes as we need. This is a really good example where we apply indirect negative feedback. So we have one current reference, and then we can just copy that current through different parts of our circuit. Extremely useful for biasing. We are coming back to this topic when we talk about generation of the DC current and voltage references.